In
Greetings, everybody. So we are continuing our videos on chaos-based image encryption, and the topic of today's video is entropy. Okay, so let's begin by reminding everybody we are talking about symmetric encryption here. You can see the previous videos as well. This means that I have a chaotic source that I'm using, for example, a discrete time chaotic system. I'm using it in order to encrypt some sort of plain text information. This can be any type of information, but it is easier to consider images, which we can then safely transmit through the public channel. And then at the receiver end, the receiver uses the exact same chaotic system, the exact same key values, so same initial conditions and parameters, in order to reverse the process and decrypt the information and obtain the original plain text back. Okay. And one of the most common processes in encryption is permutation and substitution. Okay. Permutation is shuffling of the pixels. This is pretty much like shuffling a deck of cards. So I disperse the pixel throughout the image. And the second step is the most important one, is substitution, where I take each pixel value and replace it with another value. Okay. And this results in the fully encrypted image. So after we perform encryption, we have a series of statistical tests in order to see how secure is this image. And one of these tests is entropy. Okay, so what is entropy? Classic measure in signal processing and information theory. What does it measure? Practically, entropy measures how much information, or if you like it a bit more crudely, how unpredictable or uncertain can be a time series. Okay. And of course, by that we mean any possible time series in the natural sciences, and this of course includes an image. Okay. So entropy for an image, for example, a grayscale image, pretty much represents how predictable is the time series of the image. I mean, knowing some part of the image, how can I predict the future of this time series? Okay, or if you like it, not the future, but let's say the rest of the time series. Okay, because there is no time scale here. So for grayscale images, what does this tell us? It tells us that, a fully encrypted image, an image that, as we can say, is fully unpredictable, like, knowing a part of the image cannot tell us information about the rest, should have a theoretical value close to 8. Okay, you can see on the bottom right here, this is a fully encrypted image. It pretty much looks like the classic snows on the TV screen. So this, we can say it's fully unpredictable or fully uncertain as an image. So it has a very high entropy, almost close to the maximum value, which is 8. Okay. On the other side, some classic plain text images like the papers here, or this block of gray boxes, has a much lower entropy value. Okay, this means that it carries, as we can say, less information. Okay, so what should we do here in encryption? In encryption, we should always obtain encrypted images that have a very high entropy. This practically means that they are like indistinguishable from like a simple noisy time series. So looking at it, it looks like noise, as you see on the bottom here. Okay, we can have no real information out of this image. So this is what we test here in the original shuffled and encrypted images. Although you will notice one thing very important. The original and shuffled images have the same amount of entropy. Now you may think that this makes no sense because the original image, reveals some information by looking at it, while the shuffled image reveals no information to the naked eye. I mean, when I look at this shuffled image in the middle, I don't understand anything from it. Okay. Nonetheless, entropy measures this information in the whole image. Okay, so rearranging the values doesn't affect the entropy because it takes the time series as a whole and computes its entropy. Okay, so the original and shuffled images have the same amount of entropy, right? Of course, there's another measure we're going to talk about in another video. It's called local entropy, and it can be used exactly to, deal with this problem of having the same entropy in the two images. But of course, in the encrypted image, bottom line, the entropy here is the highest, almost close to the theoretical value. Okay, so this is what we should always obtain from a good encryption. Okay. And of course, the exact same thing happens with color images. We have 3 channels. So as you can understand, we measure the entropy on each individual channel, red, green, and blue. Okay. The difference here is that we perform encryption in a very specific way. We first combine all the channels together and shuffle them together and encrypt them, all of them together. And this is why in this case, the plain text and shuffle channels don't have the same amount of entropy. And this is because we first combine all the channels together and then shuffle them. Okay, so the shuffled red channel, for example, ends up with some pixels from the green and blue channels as well. And the same holds for the green channel. For example, the green channel, the shuffled one has some pixels from the red and blue channels. Okay. And this is why they have all of them a much higher entropy compared to the plain text. Okay. But nonetheless, in the final case, the encrypted case, red, green, and blue channels should always showcase the highest amount of entropy. Okay. Which is 7.99. Okay. It's very close to 8. So again, whether you have a grayscale or an RGB image, the result of the encrypted ciphertext should always have a very high entropy. Okay. So this is it for our entropy analysis. And in our next video, we are going to discuss about the local entropy analysis, which is a bit more specific measure for images. So I will see you in the next video.